Assalamualaikum, I'm Hazarul. Today I'll be presenting a critical evaluation of gait and motion analysis, specifically focusing on how our bodies adapt their kinematics and kinetics when faced with different physical and environmental challenges. So we will look at three specific conditions: the increased load from obesity, reduced stability due to frailty, and the sudden stress of unplanned gait termination. The references for the studies discussed today are listed here. First, by Hassan, the title determined the kinematics and kinetics parameters associated with bilateral gait patterns among healthy, awake, and obese adults. The second, by Jian et al. The title Gates and kinematics and kinetics characteristics among older adults with varying degree of frailty across sessional study, and the third by Kwon et al. The title Kinetic and Kinematic Analysis of Gait Termination, a comparison between planned and unplanned conditions. Evaluation framework and methodology. To understand this adaptation, we evaluate the data through two analytical perspectives or lenses. Lens A is kinematics, which look at the geometry of motion, specifically spatial temporal parameters like velocity, as well as joint angles and range of motion. Lens B is kinematics, which examines the causes of movement, focusing on ground reaction forces and joint moments. So our evaluation synthesized data from three distinct studies. For obesity, we analyzed data from Hassan, who used a pressure mat to capture two-dimensional velocity and width parameters. For Frailty, we look at Jian, which utilized 3D motion capture and force platforms to correlate critical frailty with biomechanics. Finally, for gait termination, we exhibit Quan, who used a six-camera 3D dimension system and force plates to compare planned versus unplanned stopping. Let's begin with obesity. The Assad study revealed that we call a high load, high stability strategy. Kinematically, obese individuals exhibit a significant cadence reductions, dropping to roughly 94 steps per minute compared to 114 in healthy controls. We also see a dramatic step with increased widening approximately 12 centimeters versus just 5.1 centimeters in healthy individuals to prevent lateral force. Kinetically, this mass has a geometric cost. The maximum ground reaction force spiked to nearly 133 kilogram in obese subjects compared to uh, 81 kilograms in healthy ones. Ultimately, this excess weight acts as a massive mechanical burden, forcing the body to adopt a slower, wider gait to prevent joint failure and potential osteoarthritis. Moving to our second population, Frailty presents a very different adaptation, highlighting what we call the Frailty paradox. The kinematic signal in Jian study show significantly reduced ankle range of motion and decreased gait speed. This shuffle gait minimized the need for explosive push of power, relying instead on compensatory mechanism like an increased hip to off angle. However, the kinetic insight here is interesting. Jian found absolutely no significant difference in joint moments between frail and non-frail groups. Our interpretation is that this lack of difference is not due to strength. Uh, Instead, frail individuals intentionally slow down the keep kinetic forces within a manageable range. They are unconsciously sacrificing velocity to preserve their structural integrity and mask their underlying muscles weakness. Finally, we evaluate how the body handles sudden environmental stress through gait termination, comparing planned versus unplanned stops as studies by Kwon et al. During a planned stop, deceleration is efficient. The body uses an anchor-dominant distal control strategy that requires lower range of motion and allows for predictable energy absorption. However, when un unplanned reactive stop is triggered, the anchor power becomes insufficient. To prevent a fall, the body urgently shifts to a proximal hip and knee strategy, utilizing a massive increase in knee range of motion. Kinetically, this shortened deceleration time result in significant spike in braking forces. The body completely bypass efficient distal control in favor of robust proximal control to arrest forward momentum. Future horizons. While these studies provide critical insights, they also have limitations like sample homogeneity and instrument constraints. To improve biomechanical validity in the future, we propose three key shifts. First, sensor fusion, integrating pressure map with variable MMUs to capture both ground reaction force and joint angles simultaneously outside of the lab. Second, moving toward a longitudinal architecture, shifting from cross-sectional snapshot to tracking progression over time to see if kinetic changes actually predict fertility risk rather than just resulting from it. And third, implementing standardized stress tests, incorporating dual task or unplanned stopping protocols into standard clinical uh, assessments. This will help reveal the hidden deficits that frail or obese patients currently mask with their conservative walking strategies. So I think I will wrap up my presentation here. Thank you for your time. Bye bye.